Right, so today we're going to move on to lecture 20, logarithmic functions. So obviously in this lecture, we want to know how to identify logarithmic functions, recognize the graph of the logarithmic functions. So the difference between exponential function and logarithmic function is that for logarithmic function, we do really care about the domain of functions. So you have to be very careful when you deal with logarithmic functions. And then grab the logarithmic function using transformations. Okay, so first I'm going to give you the definitions of logarithmic functions. I will talk about, again, the idea that logarithmic function and exponential functions are inverses of one another. And then later, as I mentioned a little bit earlier, we do care about the domain of a logarithmic function. So we're going to spend a little bit of time on finding the domain of logarithmic functions. Okay, so the definitions here. A logarithmic function is a function of the form y equal to log So this stands for log, logarithmic, or logarithm for that matter. A base A. So this probably a new notation. Probably this is the first time you say this. Of x. If and only if a to the y equal to x. All right. So the notations that you see here for logarithmic functions consist of three different parts, but they have to go together. Okay. The first one is log. There will be another notations related to something called natural log functions that I will introduce to you a little bit later. But here for logarithmic functions in general, you have to include log, the base, okay, and then the variable to go. Okay, they have to go together. If you just write log base A and do not include anything related to x, that's wrong. Okay, so three parts, but they go together. All right. And again, logarithmic functions and exponential functions are inverses of one another. So you can go from one logarithmic functions to another exponential function. So they go back and forth like that. And similar to exponential function we talked yesterday, the base A here has to be different from 1 and greater than 0. Okay, so that's the conditions that we need to impose. So this base A and this base A are the same. Where A is greater than 0 and A different from 1. Right. So for the logarithmic function, we do care about the domain of the functions. Remember what I mentioned about three parts of logarithmic functions, the log part, the base part, and the thing related to the variable x. So this variable or whatever you have attached to the first two parts has to be greater than 0. That is the domain of the function. So this x will be greater than 0. So later on, we will deal with a more complicated attachment to the first two parts, which can be like 2x minus 3 or x squared plus 7x minus 5, something like that. Right, whatever you have attached to the first two parts of the function, that's going to be greater than 0. Okay. So here the domain is that x greater than 0. Or from 0 to positive infinity. So the domain will change depends on the logarithmic functions that you are dealing with. Again, I want to mention that the logarithmic functions y equal to log of base a of x is the inverse functions of the exponential functions. So now in this particular context, I start out with y equal to log of base a of x. So the inverse is going to be, if you do like the inverse procedure to obtain the inverse functions, I'm going to write this. The inverse of this function is a to the y equal to x. But you remember in the procedure to obtain the inverse functions, you have one step that is interchange between x and y. So x become y, y become x. So therefore, instead of writing this, we can rewrite this as y equal to a to the x. Okay. And from yesterday, like 2 lectures ago, when we talk about inverse functions, you know that the graph of the original function and the graph of the inverse function are symmetrical with respect to the line y equal to x. Similar to the case of logarithmic functions and exponential functions, you have that the logarithmic functions and inverse functions, the graphs are symmetrical with respect to the line y equal to x. For instance, you have the functions, the logarithmic function log of base 2 of x, and the inverse function is 2 to the x. Okay, they symmetrical with respect to the line y equal to x. Similarly, you have the functions y equal to negative log of base 2 of x. Okay, so log of base 2 of x, you do reflections with respect to the x-axis. So here, we reflect it, get this. And then the corresponding inverse function is 2 to the negative x. Okay. So they are symmetrical with respect to the line. You with me on that? We're gonna, of course, do a little bit of transformations a little bit later. And we're going to manipulate logarithmic function and exponential functions so that you can go back and forth between the two target functions. Okay. But for now, I hope that this give you some idea that, let's say this is the original function, the graph of the original function, this is the graph of the exponential function, and they are symmetrical with respect to the line y equals x. All right, so similar to the activity that we did yesterday, we're going to write out some properties related to logarithmic functions. So if you go back to the note yesterday, when we talk about the properties of exponential function, either exponential growth or exponential decay. And remember, I point out to you that if we consider logarithmic functions, domain and range to be swapped. Vertical asymptote and horizontal asymptote be swapped. X, Y intercept will be swapped. So you will see that here in the properties of logarithmic functions. Okay. But first, I want to mention that the logarithmic function is going to be one-to-one function. Therefore, you can find the inverse functions. So this is one-to-one. Now the domain is x greater than 0. So in this particular context, right, depends on the different function, you will have a different domain. But here we are considering y equal to log of base a of x. So the domain is x greater than 0 or from 0 to positive infinity. The range is from negative infinity to positive infinity. Right. So range and domain swap between logarithmic functions and exponential functions. Exponential functions, no vertical asymptote, but for logarithmic function, you always have vertical asymptote. In this case, is x equal to 0. Because you exclude 0 from the domain here. Therefore, x equal to 0 is the vertical asymptote. Again, it depends on the function you are dealing with. You can do horizontal shift or vertical shift, and then you can have a different vertical asymptote. In this case, vertical asymptote is x equal to 0. And for horizontal asymptote, there is no horizontal asymptote. X-intercept is always have one x-intercept. In this case, going to be 1, 0. So in this case, there's no y-intercept, but it's not always the case. It depends on the function. You may have one y-intercept. So let me note that here. So always not always here. Let me be careful here always, but different value. So in this case, may have 1 on no y-intercept. So it depends on the functions of consideration. All right, so let me show you something. So if you go to your, you can use a computer software, you can use your phone, or you can use a physical calculator. You will see that there is. All right. So there are two special notations that I want to point out to you. The first one is the LN notations, and another one is LOG base 10. Or some of your calculator, you have just LOG. That indications that is log of base 10. Okay. So I want to point that out to you. If you open your your phone, you can see that, or the calculator app on your phone. So the special notation is log of base e of x. This can be written as ln of x. This is called the natural log or natural logarithmic functions. It gets used a lot in mathematics and physics. ln of x. The next special notation is log of base 10 of x, or just log of x. This is called common logarithmic functions. This notation appears more often in chemistry and biology. And from now on, anytime I want to indicate natural log functions, I'm going to use ln of x. Anytime I want to talk about log of base 10, I'm just going to use ln. You with me on that? Okay. Now, as I mentioned earlier, we care a lot about the domain of the logarithmic function. So therefore, the next concept, we're going to spend some time on finding the domain of a logarithmic functions. So here, if you have log of base a of something, all right, so again, the logarithmic function has three parts: the log part, the base part, and whatever attached with the first two parts. And that the three dots are going to be greater than 0, and that is the domain of the functions. Then the domain of the function is right, so this dot greater than 0. Let's consider some logarithmic functions. So the first function here is log of base 2 of x minus 1. Again, three parts that we need to consider: log, base 2, and the whatever attached to the first two parts. This is going to be greater than 0 like that. Okay, so x minus 1 is greater than 0. That is the domain of the function. So x minus 1 greater than 0 or x greater than 1. So the domain of the function is x greater than 1 or from 1 to positive infinity. From this, you can also conclude that the vertical asymptote is x equals 1. Now, the second function is natural log of a log of base e, natural log of 2 minus x. Okay, so the 2 minus x is greater than 0. And you solve this inequality and you get 2 greater than x, or x is less than 2. So the domain of the function is, so in this case, I use g for the function, is x less than 2 or from negative infinity to 2.
And you can also conclude that the vertical asymptote is x equal to 2. The next function is the common log function. So log or log of base 10 of 5x minus 3. So the 5x minus 3 is greater than 0, or 5x is greater than 3, or you have that x is greater than 3 over 5. And the domain of the function h is x greater than 3 over 5, or from 3 over 5 to positive infinity. And you can also conclude that the vertical asymptote is x equal to 3 over 5.
So far. Now the next function is log of base 5 of x minus 7 plus 3. Now, when you analyze this function, you're going to see this, right? Again, log function, 3 parts. Log part, the base part, and whatever attached to the first 2 parts. So the domain of the function is x minus 7 greater than 0. You may wonder what happened to the plus 3. So the plus 3 is there for transformations. You shift the functions up by 3 units. You with me on that? Okay. So in finding the domain of this function, you don't care about the plus 3. You okay with that? Okay. So x minus 7 is greater than 0 is the domain of the function.
In this case, x is greater than 7, or dh is x greater than 7, or from 7 to positive infinity. You can also conclude that the vertical asymptote is x equal to 7.
Similar to example D, the function in E is natural log functions of 3 minus 4x. Okay. So 3 minus 4x is greater than 0. That is the domain of the functions. The negative one is there for transformation. You shift the function down by 1 unit. Good. So 3 minus 4x greater than 0 is the domain.
So 3 minus 4x greater than 0. Or you do 3 greater than 4x. And to solve for x, you divide both sides for 4. You get 3 over 4 greater than x, or x is less than 3/4. So the domain of h is x less than 3 over 4, or you can write from negative infinity to 3 over 4. And the vertical asymptote is x equal to 3 over 4.
Any questions? Okay, next we're going to do some transformations to logarithmic functions. Now, in the first graph, I have the original functions of the form ln of x. I do 2 vertical transformations. You move up by how many units? 1, 2, 3, 4. Did I count it correctly? Yes. And then move it down by 1, 2, 3, 4. So 4 units up, 4 units down. Yeah. So here how you present the answer.
So here you move it up by 4 units. So you have y equal to ln of x plus 4. Now you move it down by 4 units. You have this to be ln of, sorry, y equal to ln of x minus 4.
Questions on the first graph. Now on the second graph, this is the original functions log base 2 of x. Now you move to the right by how many units? 1, 2, 3, 4, 5 units to the right. And 1, 2, 3, 4, 5 units to the left. Okay, so this is how you present the answer. Move it to the right by
5 units. You have this to be y equal to log of base 2 of x minus 5.
because you move it to the right or horizontal shift, it affects the x value. It's 5.
And you move it to the left by 5 units. The answer is y equal to log of base 2 of x plus 5.
Plus 4, not 5.
1, 2, 3, 4, 5.
And move it to the left by 5 units. So it's 5 here, 1, 2. Oh, yeah.
So vertical shift, horizontal shift. Now in the next part, we're going to do reflections. Okay.
So the first graph, you do reflection with respect to the x-axis. So reflection with respect to the x-axis, the y value got changed. Positive y become negative y, negative y, positive y. So the whole thing get affected. So ln of x become negative ln of x.
So this y equal to negative ln of x.
The next graph, you have reflection with respect to the y-axis. Positive x become negative x become positive x.
So the answer is y equal to ln of negative x.
Now number 3. You have two transformations here, given the original function that is log of base 3 of x. You have one transformation that is you move it to the left by 4 units. Okay. And you reflect it with respect to the y-axis. Good, so two transformations. So what should we choose here? Reflecting with respect to the y-axis and shift it 4 units to the left. So B is the choice.
Any questions?
Now, number four, talk about the different properties of the logarithmic function, in this case, ln of x. Okay. So think about it a little bit. There are 6 options here, but it's not going to be all 6. Okay. Think about it a little bit. So let's say A, the graph has a vertical asymptote of x equal to 1, true or false. Right, so you analyze this function as well. So the domain is x greater than 0, so x equal to 0 is a vertical asymptote. So vertical asymptote of x equal to 1. So A is not going to be the option. So I, 1i, and 2i not going to be choice. The graph has a horizontal asymptote. So we learned that for logarithmic function, there's no horizontal asymptote whatsoever. So 3 is not going to be the choice. So 4 should be the